So let's talk about that more difficult case. So again, SUPG, but now with higher order basis functions. Now we still have our normalization with respect to the maximum magnitude of A, the L infinity norm of A. And we have here our normalized bilinear form. And in this case, this new term here does not drop out. We can't neglect it. For the higher order basis functions, this is not equal to 0. Now I have to be a little bit careful now. I have to actually write this as the sum over different elements. And then we do this L2 inner product on the element domain, right? Because the second derivatives of piecewise continuous function, sorry, of a continuous function, but that is allowed to have a kink from element to element, we couldn't integrate that across the edges. We can only integrate that on the volume of an element. Okay, so let's single out this additional term and let's see what happens to our coercivity estimate. So we have the new term tau SUPG divided by alpha, and I'll focus on a single element. Minus actually times kappa times the Laplace operator of phi. Okay, so this seems to be a bit of a difficult term to handle. Excuse me, A dot gradient of V. So this seems to be a bit of a difficult term to handle. It's a term that we haven't really seen before. It's non-symmetric. It has higher order derivatives. Yeah, so how are we ever gonna wedge this into a norm? Well, the first time we started talking about proving coercivity properties, I also proposed a number of inequalities. Cauchy-Schwarz inequality, the Poincaré inequality, and Young's inequality. Now, we used the Poincaré inequality a couple of times. That was where we relate derivatives, so integrals of the derivative to the integral of the function itself. So we often needed this to replace to replace a norm like this, where we're integrating the gradient to an L2 norm or partial L2 norm. Also to bound it with the H1 norm, for instance, which is a combination between the L2 norm of the function and the L2 norm of the gradient. So we saw the Poincaré inequality a couple of times. We also used Cauchy-Schwarz mostly for boundedness properties, but we haven't really discussed the Young's inequality yet, and that's precisely what's going to help us treat these types of terms. So Young's inequality is the following statement. That is, if I have an inner product, and it really actually doesn't mean what kind of inner product. We're going to be talking about L2 inner products, but this is more general than that, of a function f and a function g, then that is going to be bound from above. And actually, because we're mostly dealing with negative terms, I'll change this directly into a negative term. And then it's going to be bound from below by 1 over 2 epsilon times the norm of f square minus epsilon over 2 times the norm of g square. And epsilon is now a free parameter. So this is going to be an inequality that is true for all epsilon larger than 0. Yeah, so I can choose my epsilon as always going to be true. And this epsilon is going to allow us to shift sort of weight between the different norms. Okay, so let's apply this inequality for the term that we have right here. And the first thing that I'll do is I'll distribute this term equally, this term tau SUPG divided by alpha equally among the first, along both slots. So I'm going to take the square root here, and I'm also going to put that one, let's move this to the right. I'm also going to put this I'm also going to put that right there. Oh, now my G moved with me. There we go. Yes. Okay, so I hope that was clear. That's the same thing, right? I can either multiply by the function or multiply by the square root times the square root of that function. Yeah, and that's particularly true because both tau SUPG and also alpha are necessarily positive values, right? Okay, so with this inner product, I'm going to define this to be f, and I'm going to define this to be g, and then I'll use the Young's inequality. And in this case, I can still keep it relatively simple because this is going to be sufficient for the choice of epsilon is going to be equal to 1. So I don't have to think about that too much yet. Yeah, but we'll actually have to use this again later, and then we have to make a different choice, a smarter choice. So what happens with this inner product after I use Young's inequality with epsilon is equal to 1? Well, that means that I can bound it from below by the negative half of the norm of tau SUPG divided by alpha A dot gradient V minus half of the norm of that second term kappa tau SUPG divided by alpha square root times kappa times delta or Laplace of phi square. You know what, and I'll jump straight into the coercivity estimate so that my functions are both going to be V. Yeah, I'm substituting the same function in both slots. And both of these are squares. Okay, now well, this term is actually not a problem at all because I had 1 times that term already from the other term in the SUPG stabilization. Yeah, so let me actually write it out a little better. I'll treat this entire term. Let's see what happens if I do the coercivity estimate of that. So then the B SUPG, let me call it like that, V comma V. So that would just be this term, right? This bilinear form term. It's going to be equal to, well, the sum over K. No, let's not worry about that yet. Firstly, we have tau SUPG divided by alpha A dot gradient V times A dot gradient V. So that gives me secondly, we have, well, this guy multiplied by that guy. And for that one, we used Young's inequality. So we have this. Does that fit? Not really. V SUPG V comma V, and now actually it's going to be larger than or equal to, right? We get this. Now these are the same terms, so we get that this is going to be larger than or equal to, well, half of this, right? That's what's left. And this should actually be then the sum over the different elements. So this is going to be the L2 inner product over the complete domain omega. And then we still have minus the sum over elements k of half times the square root of tau SUPG divided by alpha times kappa times the Laplace operator of V. Okay. So this is a negative term. This is a negative term that looks like a norm. So how are we going to treat a negative normed quantity? Well, this term also looks quite a bit like the first term, right? We have a kappa here. This is a diffusive term. Well, this also involves a diffusive operator. So what we'll try to do is we're going to coalesce this term with this term. And the way that we'll do that is we'll use an inverse inequality. So that's a new type of inequality that we haven't talked about yet. And there's a whole bunch of different inverse inequalities. And inverse inequalities are based on the fact that we're dealing with a discrete function space. So inverse inequalities actually are not satisfied in H1 or L2 or whatever. They're only satisfied because we're dealing with a discrete function space, or a finite element function space. And the inverse inequality that we're going to use right now is the following. We're going to say that the L2 norm of the Laplace operator of a function v is going to be smaller than or equal to a constant, which I'll call Ci for inverse inequality. And then we know that it's, by analysis, we know that this is going to scale inversely proportional to h times the norm of the gradient of that function. Now, and again, this in general is simply not true. It kind of looks like a Poincaré inequality, but it's the opposite of a Poincaré inequality. So let me, as an interlude here, say Poincaré would be that we take the integral of a function v, and that's going to be bound from above by a Poincaré constant times the inner product of that function, the gradient of that function. So now we see that from left to right we have an increase in the differential order, but here in our inequality that we're trying to enforce right now, we have a decrease of the differential order. So this would be an inequality that looks a little bit more like trying to say something like the gradient of v is bound from above by some constant times the function itself. And that is typically not true. This is certainly not true for all functions v in H1. Then it's certainly not true. But we're not dealing with all functions in H1. We're dealing with a very small subset of functions in H1. And for those functions, you can actually prove that this is true. But it will actually, this estimate will get worse and worse as you mesh refine, because as you mesh refine, you go closer and closer to the true function space H1. So we have this H1 in here as well. Yeah, and this is not meant to be a hand-wavy argument. You can actually compute this constant. The way you would go about doing that is that you interpret this to be, well, this is equal to stiffness matrix times the function, the vector of coefficients, and actually also the vector of coefficients here. And this one is going to be equal to the mass matrix. And then you can identify this Ci h minus 1 as the smallest eigenvalue of a generalized eigenvalue problem, much in the same way as we talked about the inf sub conditions as well. And because the eigenvalues of the stiffness matrix decrease at a higher rate than the eigenvalues of the mass matrix, we have this scaling with respect to the mesh size. Okay, so, but that is not the inverse inequality that we're going to use. This is the inverse inequality that we're going to use. And you would also be able to compute the corresponding Ci value also with sort of an eigenvalue problem. And the nice thing is that we only need this on each element, right? So I can locally assemble these matrices on each element, and then it will be a very cheap operation. It's going to be an eigenvalue problem with really just a handful of degrees of freedom. So now suppose that I can make use of this inverse inequality. Well, then I can bound this term from below. Yeah, this is a negative term. So the way that we would go about replacing that is if you multiply something by an inequality by a minus 1, you get a minus here, you get a minus here, but you also flip the sign. And then we can see that we can continue our inequality saying the following. plus the sum over k times half the square root of tau SUPG divided by alpha times, and now we get these guys in there, like this, kappa gradient of v. Okay. What I'm struggling with right now a little bit is I'm thinking whether I can replace this sum over k by elements k now simply by the inner product of the thing on the whole domain. Oh, before we get there, this is definitely a minus. Yeah, we can, because there's a square. Okay, sorry. So this is going to be equal to simply this. Okay. So now we still have a negative contribution of a normed quantity right here. But now this normed quantity looks, well, an awful lot like the thing that we do have. So let's consider the coercivity of the complete bilinear form. We have B, V, V is going to be larger than or equal to the norm of, well, the square root of kappa divided by alpha times the gradient of V. That's our original term right here. Plus, well, this stuff. Okay, so now we see that we can combine this term with this term. And after we combine those two terms, we have to make sure that the result is always going to be larger than or equal to, well, some positive normed quantity. So, based on that idea, what I'll do is I'll say I'm also going to bound tau SUPG from above. And I'm going to say if tau SUPG is always going to be smaller than or equal to h square divided by ci square kappa. Okay, what happens if I make this assumption or this requirement on my stabilization parameter? What happens with that last term? So we have now I feel like this should be in the square root. Is that true or not? Is that true? Yeah. No, sorry. Or this should not be a square. Yeah. So in this inequality, I can pull this inside, and after that, I'll square both sides. Yeah. So then this is simply inside with the square. Yeah. Or alternatively, you first square the whole thing, and then you can also pull it inside, but then the square is already outside. Okay, so we have this, we have the square root of tau, which gives us, okay, square root of 1 divided by alpha times h divided by ci square root of kappa, that's the square root of tau, times ci divided by h times kappa times the gradient of v. And that's going to be equal to cancels, 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 square root, right? So it's going to be equal to the square root of kappa divided by alpha times the gradient of v squared. Yeah? And since this is an inequality smaller than or equal to, this is always going to be larger than or equal to. Because there's a minus sign there. So now this is the same term as we have over here with a half. So we get again v comma v is larger than or equal to half of that norm plus half of our tau SUPG divided by alpha square root a dot gradient v. Okay, so now we have our coercivity statement. The b bilinear form v comma v is going to be larger than or equal to, well, some constant times a normed quantity. And now we also have an upper limit of our stabilization parameter. So from our first video, we saw that we have a certain expectation of what we want our tau parameter to behave, or how we want our tau parameter to behave. And now additionally we have an upper limit. So we have to make sure that we construct a tau that kind of satisfies both. We want what has to satisfy our limit, and at the same time we would like it to behave in a different way. So the way that we typically construct our stabilization parameter right now is with the following asymptotic scaling technique, is what we call this. So we choose tau SUPG as 1 divided by the square root of 2 times a divided by h square plus c square kappa divided by h square square. And this is a funny type of equation. It kind of looks like a harmonic mean, but then also not entirely, because we have sort of a square root wedged in there as well. But the way that we construct a function like this, and you can verify this for yourself, but the way that we construct it like this, it satisfies certain limiting requirements, and it also satisfies certain maxima. In particular, this means that tau SUPG is going to be smaller than or equal to either one of these expressions. You can verify this yourself, but this construction is such that it is going to be bound from above by, well, 1 divided by the square root of the square, so we actually get h squared divided by c squared kappa. But additionally also tau SUPG is going to be bound from above by the second one, h divided by 2a. So we have here automatically the bound that we just required. Additionally, we can also obtain certain limits of this tau expression. In particular, if I have a limit, let's write it differently, a limit of the magnitude of a times h divided by kappa goes to 0, then this tau SUPG is going to limit to this one. This one is going to be approximately 0, and this one is going to be non-zero. So you would end up with that expression. So that means that this is going to be equal to, well, h over 2 c squared kappa. And that's kind of what we want as well. If our advection becomes very, very small, well, then we don't want to have this advective term anymore, right? We needed this limit only in the case that we had a very large alpha. If we have not so large alpha, so not very large advective dominance, well, then we don't even really need our SUPG term at all. And we really wanted that scaling that we proposed in the first video only in the case, so this one, we wanted this only in the case where we have a large alpha, so a large advective dominance. And that is also precisely what this tau SUPG satisfies. So in the limit of h divided by kappa goes to infinity, so we have a very large advective dominance, then tau SUPG will actually limit to the first term in that harmonic mean. So this is a smart construction of a function tau that satisfies very naturally certain limits in terms of maxima and in terms of advective dominance that both satisfy what we would want in these limits. That would be this one. This. That's what we wanted in the limit of advective dominance, and also what we need. That was this one. Now, the last thing that I would still like to point out is that I've secretly wedged in this factor of 2 over here. That's really not something that we discussed about yet, because what we really only said was we wanted the scaling to be h divided by a. So I added a 2 here, and I think that kind of also illustrates sort of an arbitrariness that we still have left. Our choice of parameter tau, well, we have certain limits and we have certain expectations, but other than that, we're still relatively free in our choice. So how do we then end up making that choice, and specifically, how do I choose this factor 2? Well, we're going to get that inspired from the physics, and in particular, we'll see that there's a strong relation between stabilized methods and fine scale models, so turbulence models in the case of fluid mechanics. And it's precisely from this perspective on the stabilized methods that we get the very specific expressions for these two different components of our tau. Yeah, so this one, and then we can also get a very specific expression of this C. We'll find that this is going to be the limits of the fine scale effects either in the advective or the diffusive dominant limit. And one last thing is then, notice that this is not just an arbitrary choice of combination of parameters. This is actually your element Peckley number. Now, I haven't really talked about Peckley numbers yet, but that's the ratio of the advection and the diffusion within a certain element size h. Okay, so far on SUPG. Next up, we'll have a look at the pressure stabilization, so PSPG.